Today we're going to talk about vectors. So a vector is a physical quantity that includes both magnitude and direction. And we've already been working with some vectors: acceleration, velocity, displacement, position. Those are all vectors. There's several different ways to note vectors. In our textbook, there's a little arrow over the symbol. You'll also see it as a bolded variable if it is a vector. I've included some examples of vectors that we're going to be working with in this next couple of units. So displacement, velocity, acceleration, position, and force. Our vector can be represented in a couple of different ways. We can represent it with some numbers, or we can also represent it with an arrow. The length of the arrow represents the magnitude of the vector, and the direction the arrow is pointing represents the direction of the vector. Let's talk about what we do with vectors. We're going to start with adding vectors. When adding vectors, there's a couple of different ways to do it. I'm going to teach you how to do it graphically and with components. So let's say that we have these two vectors. We have vector A and vector B, and we want to add them together. We're going to add them, what we usually say, like head to toe. So you're going to take your A vector and you're going to place it here. And then your B vector is going to be placed at the end of A. So the beginning of B goes at the end of A. And then your resultant vector, so this is what's the resultant is the name for the total of the two vectors added together, will be drawn from the beginning of the first vector to the end of the last vector. Now notice that we can add these two vectors in any order because addition of vectors follows our rules for addition of just numbers in math class. So it's a commutative property. So we can take vector B and add vector A, and we get the same resultant. You can see that those blue arrows are the same length. One thing I always like to say that vectors are not recyclable, because a common mistake is to draw the first vector like this, the second vector head to toe, and then draw the resultant vector in this direction, which makes like the recycling arrows where they're all pointing towards each other. That's not how the resultant arrow should be drawn. It should be drawn from the beginning of the first to the end of the last. So if you draw out your vectors and you have a recycling symbol, that is not the correct way to do it. Here I just have an example, another example of the commutative property. So I've taken these different vectors and I've added them in different orders, and we can see that all three of these red vectors are the same. Now let's talk about subtracting vectors. So to subtract a vector graphically, you're going to take the first vector. So let's say that we have A minus B. You're going to take the first vector A and you're going to place it, you're going to draw it, and then you'll take vector B, and when you subtract vector B, you're basically going to add the same vector, but it's pointing at 180 degrees from its original direction. So you can see that I've taken B and I've flipped it 180 degrees and added it to the end of A. And so now I have A minus B, and this is my resultant, A minus B. Notice that if I do it the other way, if I do B minus A, then I start with B, I add A at 180 degrees, and this is my resultant for B minus A. Subtraction is not commutative, so it does matter what direction or what order you subtract them. You know, like 5 minus 2 is not the same as 2 minus 5. It's the same magnitude. You would get 3 for both, but you would get a negative for one of them. So it's the same idea here, where you get the same magnitude vector, but it's pointing in the opposite direction. All right, so then we also need to know how to multiply vectors by a scalar. So a scalar, remember, is just a number that has no direction. So examples of scalars are time, mass, distance, those kind of things are scalars. And so if I have a vector of 2 and I multiply it by a scalar of 3, the direction doesn't change, only the magnitude changes. So when we multiply a vector by a scalar, only the magnitude is going to change, not the direction. All right, let's talk about how to, two different methods for adding vectors. We're going to start with the graphical method. So the graphical method would be to draw a scale drawing of the vectors. So let's say that we have our these three vectors and we need to add them together. So we would add them head to toe like this, and you would be like measuring out the angles and the lengths with your ruler and your protractor, and then you draw your resultant from the beginning of the first to the end of the last. Then to figure out what the resultant is, you would take your ruler and you would measure the length of that resultant vector, and you would take your protractor and you would measure the angle of that resultant vector. So that is the way that we add them together graphically, is drawing a scale drawing of those things. You'll do that occasionally, but usually you're going to use the component method to add vectors. So the method for drawing components there is to, let me see if I just ended that. Okay, is to first use trig to break each vector into x and y components. Then you're going to add all of the x components together, and then you'll add all the y components together. And then you're going to take that resultant x component and resultant y component to find your resultant vector. Now, just a reminder for you, those trig functions that we're going to be needing are sine is equal to opposite over hypotenuse, sine of theta. Cosine of theta is equal to adjacent over hypotenuse, and tangent of theta is equal to opposite over adjacent. So make sure you brush up on your memory of those things. It may have been a while for you. And when we have these vectors, we're going to be turning them into, basically turning them into 90-degree triangles. So let me show you what that looks like. I'm going to do a simple one real fast. So let's say that we have this vector right here. Goodness, it's hard to draw a straight line on this thing. Okay, there we go. So there's one vector there, and we want to add this vector here. Okay, so these are my vectors. Now I'm going to turn them into 90-degree triangles. So I've made these vectors so that they have perfect x and y whole number components. So here's my y component of A and my x component of A. And we can see that this is 1, 2, 3, 4, 5, 6, 7 blocks. So there would be 7 units there, and then 4 units here. So this vector goes 7 units up and 4 units to the right. My second vector here is going to be, this is going to be my x component. And usually you draw the components with dotted lines. The thing that I'm using to do this doesn't make that super easy, but okay, so 1, 2, 3, 4, 5, 6, 7, 8 blocks here, and 3 blocks here, but notice that this is a -3 because it's going down. So our first vector has a y component of 7, and our second vector has a y component of -3. Now I can see pretty easily that my resultant vector here is going to be this line right here. So when I draw the components of the resultant, I draw these lines here. Now I can see that that's 4, +4, as my component for my resultant, my y component. And I got that by drawing it graphically, but I also got it by adding these two y components together, 7 up and 3 down. And then my x component here is just going to be 4 plus 8, so that's 12 units. So my and I could also count that to see that that's 12 units. Now to find everything out about my resultant vector, I would need to find my angle theta here, and I would also need to find the length of the hypotenuse of this resultant triangle. So To find the length of that, I'm going to do the square root of 12 squared plus 4 squared. And oh goodness, that is 12.6. And whatever unit, I didn't pick any units. And then to find my angle, I would do theta is equal to the tan inverse of 4 over 12. And we usually measure these angles from, oh, it must be in, you want to be in degree mode for this whole unit. So make sure that you put yourself in degree mode in your calculator. So this is going to be 18.4 degrees is that angle. So we'll talk about how to express that angle soon as well. So that's how we add vectors with components. Now there are several different ways to express direction. The way that we have done it, you've probably done it in math class, is by expressing it from the positive x direction. So this is the positive x direction. So if you had this angle here, you would say maybe that's 45 degrees. If you did this one here, maybe it would be 200. Or you might do one that's like negative 30 or something like that. So that is one way to express the angle. Sometimes if we're talking about velocities or displacements on the Earth's surface, it makes more sense to do our direction with respect to the compass rose. So a lot of times when we're doing problems where we're doing like something on the Earth's surface, we're going to use this one. So here's our compass rose. And let's say that you have, I don't know, a plane flying in the air or something, and it's flying this way. You can express this a couple of different ways, but this is the angle we would probably choose. And you would say, let's say that this is 35 degrees. You would say that this is 35 degrees east of north. You could also say that it's 55 degrees north of east. It doesn't really matter that much. And so we could do that for any of these directions. If you have a direction that's exactly east or exactly north, then that's all you need. You also may have a direction like this one. If this is a 45-degree angle here, then this would just be called southwest. There's also, this isn't used very often in your physics textbook, but if you're using a compass, the angles will be given from north. And I just wanted to mention that because that's how it's done with a compass, where the angles written on there are measured from north. Okay, so let's do a couple of examples. Let's add the following vectors so that you can see how this is done. We're going to start off with adding these two vectors together. So we are going to do 10 meters. I'm going to go back to purple here. 10 meters at 39 degrees north of east. So that's 10 meters. And this is 35 degrees north of east. And then we're going to go 7 meters at 28 degrees south of east. So that might look like this. This is 7 meters. And this is 28 degrees south of east. So now I can use trig to figure out what my legs of my triangles are. And down here I can do the x is 10 times the cosine of 39 degrees. I think I wrote 35 there. That's supposed to be 39. Okay. 10 times the cosine of 39 degrees is equal to 7.8 meters. Then my x or my y component here would be 10 times the sine of 39 degrees, and that's equal to 6.3 meters. And then my x component up here is 7 times the cosine of 28 degrees, which is 6.2. And then my y component is 7 times the sine of 28 degrees, which is 3.3. So now when I draw my resultant, and I made this a little bit messy, I'm sorry. So here's my resultant. Oh, that should be a straight line or a solid line. Okay, there's my solid line there. And then I have my x component here and my y component here. So to find my total y component, I'm going to do my 6.3 minus, oh, I forgot my subtraction sign there. That is a negative because it's down. And when you do it like this, where you're just making them all 90-degree triangles, and you're calling this 28 degrees and not negative 28, all of your components are going to be positive. And then you just have to remember to put the negative signs on there. The other way to do it would be to do the actual math with the angle measured from the positive x-axis, so you wouldn't miss the negative signs, and that's fine too if you want to do it that way. Okay, so this would be 6.3 plus 3.3, so that's 9.6, and then meters. And then our x component is going to be 7.8 plus 6.2, and that gives us 13.8 meters. So now to find my resultant here, I'm going to take the square root of 13.8 meters plus, squared, plus 9.6 meters squared. And that gives us 16.8 meters. So that's the length of my vector. And then I also need to find my angle here, theta. So my theta is going to be equal to the tan inverse of 9.6 over 13.8. And that gives us 34.8 degrees. And that's going to be north of east, because this is east and it sweeps to the north. So that would be my full resultant vector. Now, some of you may be asking, can't I just use the, oh, I lost my second problem somehow. I wonder how that happened. Okay, that's okay. Some of you may be asking, why can't I just use like law of sines or law of cosines to solve these? And you can definitely use that if you'd like to, but you definitely need to know this method, because there will be times where you'll have more than two vectors you're adding together. So for example, if you had this vector and then this vector and then this vector, then this doesn't make a triangle when we draw this resultant. So you'd have three different y components to add together, three different x components, and to get your x and y components of your resultant. So using law of sines and law of cosines is okay, just make sure you know how to do components so that you could do a problem like this. That's all I have.